Robert Spengler, who is currently the director of the Paleoethnobotany Laboratories at the Max Planck Institute for the Science of Human History in Jena. Prior to this, he has been a visiting research scholar at the Institute for the Study of the Ancient World through New York City, through New York City University, as well as the German Institute for Archaeology at the Freie Universität Berlin. It's very in small print, therefore I'm kind of happy. He defended his PhD at Washington University in St. Louis, so it's a home game for you also. Well, that is another Germanism, I'm sorry. He is studying paleoeconomy and ecology of Central Asia from the 3rd millennium BC onwards and has ongoing research projects in Kazakhstan, Uzbekistan, Turkmenistan, China, and Mongolia, where he has been recently. But he is not only flexible, but he has a global perspective. He will talk about rethinking early agriculture, setting the stage for the Anthropocene, and I think we are here just in the right place to discuss those things.
Well, it is wonderful to be back in St. Louis after quite a few years. So after that wonderful introduction to the Max Planck Institute for the Science of Human History in Jena, Germany, I will be following up with a quick discussion of a number of interrelated projects that I am working on along with my colleagues in Jena, and also Dr. Natalie Mueller, who will be presenting on some of these collaborations in just a little bit. And they're interrelated projects looking at the origins of agriculture and the intensifications of agriculture in the archaeological record, and really thinking about this idea of agricultural intensifications as the foundations for what eventually would become the Anthropocene. So I think we all can look at this image and realize this is a dramatically, anthropogenically altered landscape, and that this picture could be taken anywhere in the heartland of America, anywhere between the 1980s and today. And it's really not even the scale of anthropogenic change in this part of the world that is impressive. It's the rate of anthropogenic change. So if we looked at the same part of the world in the 1930s, it would look something like this. And as recently as the 1850s, it would have looked something like this. This is a massive scale, highly rapid agricultural transition that fits over a demographic shift and major cultural changes in this part of the world. Historically, we know how this plays out. It's largely tied into innovations in agriculture. There should be more slides coming up, but they're not. But they're largely tied into innovations in the agricultural system that are driving new transitions in the Midwestern parts of America. So in the late 1920s, you have new agricultural crops being put into place. These are the hybrid mazes. In the period after World War II, you have, again, a new set of hybrid crops coming into play, high nitrogen fertilizers, mechanized farming, rapid transformations of the landscape. And I'll also quickly note that in the last 20 years or so, there's a whole new agricultural innovation in the central parts of America. So this is historically documented, but as archaeologists, we're interested in looking at agricultural transitions and their associated demographic shifts, so human population changes in the archaeological record. And I'll note that these processes are not new to the historical period. There are major cultural changes that are affiliated with agricultural intensification throughout human history around the world. And this is one of the things that myself and my collaborators are looking at, and I'll come back to this topic at the end, but I want to quickly start off by looking at some of my work that is attempting to find similarities or linking threads between the origins of agriculture around the world. So I think most of us are familiar with the fact that the domestication of agricultural crops played out in very different geographic regions around the world. There have actually been up to 16 distinctive spots where the domestication of plants may have independently played out without interaction with other regions separately throughout the last 10,000 years. These regions are in ecologically very diverse areas, climatically very different areas. Culturally, these places are very distinct from each other, and the plants themselves are quite diverse. So finding a similar thread that unites all of these areas is difficult beyond, obviously, that humans are involved in this process. But I would argue that there is actually a similar thread, and it is the need in plants to disperse their seeds. So I would argue that most of, if not all of, the earliest plants to evolve traits of domestication, these traits are tied into seed dispersal processes. And humans happen to be the most successful seed dispersers on the planet. So what this means is plants, they are not mobile in and of themselves. So in order to move, to colonize new areas, they need to move their seeds. And they need to have mechanisms or ways to do this. In addition, if a plant drops all its seeds directly below the parent plant will probably outcompete its entire lineage. And if it's an annual crop, sibling competition will quickly wipe out a large portion of that parent plant's offspring. So the seeds that evolve better traits to move, or the plants that evolve better traits to move their seeds, are more evolutionary adaptive. And we know this is the factors that play out with the earliest domestication events that have been studied. So the crops that have been most heavily studied in the archaeological record, interesting, are the large-seeded annual grasses. So these are our cereal crops, and this is actually the progenitor for our modern barley. And we know that its seed dispersal process in its wild state is actually a brittle rachis. So the actual stem at the tip of each individual seed, when the seed is ripe, it becomes fragile, and when the plant blows in the wind, these seeds shatter off and they can move up to 2 meters away from the parent plant. But this is actually a weak seed dispersal process, and because it can only move the seeds so far, it leads to dense stands of wild plants that can be as dense as agricultural fields. And this is an important topic that Dr. Mueller will come back to in a little bit, as far as which plants humans selected for early on. So when humans first started harvesting these plants, the plants evolved tougher rachises in order to retain their seeds so that humans then could spread them more successfully over larger areas. We know that there's essentially a similar process at play with the domestication in large-seeded legume crops. So pods, often in their wild state, will explode, sending seeds out, in some cases up to 2 meters away from the parent plant again. And the chickpea here, with its wild and its domesticated form, the pod actually shatters off of the parent plant. These are the first traits lost when humans start cultivating these plants. So the switch from a wild seed dispersal process to a human-induced seed dispersal process is the key for all of the plants that have been heavily studied. But this is about as far as scholars often take this discussion. And I find that fascinating because when we look at fruit domestication, a fruit in the wild is actually an evolutionary adaptation for seed dispersal. It's an enticing mechanism for the plant to convince an animal to consume its seeds, which then are piggybacked in the stomach of that animal to a new area where they're then deposited. So in the pepper here, we have a switch in the wild form of a bird disperser to a human disperser, equating larger fruits. And if we look at the fossil record from an evolutionary ecology perspective, the evolution of larger fruits plays out repeatedly in the fossil record when enticing larger mammalian dispersers to consume seeds. So this is the progenitor for many of our squashes, or things that we would often call a pumpkin. And actually there's a number of these wild populations that all played a role in this through through hybridization events, but this is obviously too big in its wild form for a bird to consume it and disperse it. Back in 1982, Jansen and Martin proposed the idea that most of the large fruits in our grocery stores evolved in the wild to be dispersed by megafaunal mammals. And most of these megafaunal mammals went extinct at the end of the Pleistocene, so the end of the last ice age. This idea was recently resurrected by Logan Kistler and his colleagues when studying the genetics of the domestication of squashes. And they noted that the wild populations of squashes are highly fragmentary today, that these are highly inbred population lines and they do not spread their genes across these populations. And this is because the seed dispersers, the wild seed dispersers that these plants evolved for, are now extinct. And they went extinct roughly 12,000 years ago. But it's not just the case for the squashes, it's the case for essentially all of our fruit crops. And my main study topic is actually the domestication of the apple right now, which is domesticated in Central Asia. And if we look at the wild apple populations in Central Asia, just like the squashes, they are highly fragmented today. They show genetic evidence for inbreeding. They do not spread their seeds, despite the fact that an apple is an extremely energetically costly seed dispersal process. So for an apple tree to produce a large amount of apples that are then dropped directly below the tree, and the seeds in them are either lost through rotting or through lack of dispersal, it's evolutionarily a dead end without large mammalian dispersers. But of course, when humans come into the picture, they then become these ultimate dispersers, crossing different lines from different populations, causing hybridization events, and really dramatically changing many of these populations. So this is domestication. So in many ways, the extinction of the megafaunal mammals drove domestication in many of our plants. So why is it that plants in their wild states would evolve traits of domestication, or traits of larger fruits, or traits to attract megafaunal mammals? So if we think of the world on an evolutionary timescale, with each interglacial phase of the last Pleistocene, the last ice age period, every plant in the northern hemisphere had to migrate across an entire continent. So the greatest migrations the world has ever seen. And the plants that could not run fast enough went extinct. So piggybacking or catching a ride in the stomach of a giant mastodon, a glyptodon, or something like a giant sloth, a mammoth, or a gumphera would be an easy way to spread your seeds, in some cases over hundreds of kilometers in one generation. So I would argue that it's not just large fruits that evolved to adopt these traits. It's also small seeds that are on plants consumed by ruminants. These seeds also evolve specific traits for seed dispersal, which is the topic that Dr. Natalie Mueller will come back to in just a little bit, and an ongoing collaborative project we have between our institutes here in St. Louis and in Jena, Germany. So in addition to her research in the lost crops of North America, there are also small-seeded crops such as buckwheat in the Himalayas that may have similar traits, amaranth in the Andes Mountains that may have evolved traits to be consumed by large mammal dispersers, and also possibly maize in southern Mexico. So I would point out that in the last 6 months or so, there's been a huge change in what we know about maize domestication, and it's largely coming out of this large-scale genetic study that was done, again, by Logan Kistler and his colleagues. But it shows not only that the domestication process in maize was extremely complex, that it evolved numerous hybridization events from different wild populations of its ancestral grass, this thing called teosinte, but also that by 3,500 BC, when maize was spreading out of its central region of domestication, many of the key traits that we think of as modern domesticated maize today were not fixed into the population yet. And this means that maize evolved on similar parallel trajectories towards modern maize, independently on two continents as it spread north and south. What's really interesting about the spread of maize in the ancient world is it is the fastest crop in the ancient world to cross lateral boundaries. It spread into North America and it spread into South America. Whereas most crops follow lateral lines when they spread, maize was able to evolve rapidly to deal with different ecological settings in very different parts of the world. And looking at a publication from just about 2 months ago, looking at archaeobotanical remains from the Atacama Desert, we can see that preserved archaeobotanical remains of maize cobs from roughly 2,500 years ago were small. They were not the high-yielding mazes that we think of in the Midwest today. In fact, highly productive mazes that look a lot like our modern mazes didn't appear in South America or didn't evolve in South America until the formative period of the Inca. Again, linking high productive agricultural crops to population demographic changes and the beginnings of political organizations or more complex political organizations and social hierarchies. But where this is interesting in the ongoing maize work being done at the Max Planck Institute in Jena, Germany, is that there were major ecological barriers that maize had to overcome as it spread into North America. The wild progenitor is a tropical grass, and it is very much not adapted for survival in North America. So this is one of my test plots in upstate New York, growing the wild progenitor of maize, which produces amazing foliage, but does not produce seeds, even if you start it over a month in advance in a greenhouse. The length of a growing season in these crops had to be cut down almost in half before it could move into northern regions of North America. And of course, there would have been cultural barriers at work as well, and many people, including my former advisor, Gail Fritz, here in the front row, have studied these in great detail. And then the topic that they are probably the most interested in is the role that the intensification of maize agriculture in North America might have played in the development of some of these political centers or the development of more complex political hierarchies and social organizations in North America, as we see with agricultural innovations in other parts of the world. And in order to get at these questions, this team is looking at carbon isotope studies on human bone collagen. I'm not going to talk about the science behind this, but essentially if you consume a large amount of maize, it leaves a carbon signature on your bones, and that signature is still there 1,000 years after the individual has passed away. This method is actually not new. It's been around for a few decades now, and there's been a massive amount of research into this topic in North America. But what is new about this study is that my colleague Ricardo Fernandez in the Max Planck Institute has actually developed a computer modeling program using Bayesian statistics that can calibrate for a large number of variables that are normally not accounted for in this process of isotope uptake. And the program also can map out through time and space the spread of maize in North America. So hopefully once the program or the data is fully integrated into this new program, it'll give us a better idea of the rates of spread in various parts of North America and potentially what some of the processes that may have led to slower rates of spread in various parts of North America might have been. So I will wrap up here by noting that there are a number of related processes at play and different projects underway at the Max Planck Institute, both in collaboration with colleagues in America and in other parts of the world, and that we are looking for essentially ancient social and cultural processes that would have built a foundation for what we think of as the Anthropocene today, or at least got the snowball rolling towards a more intensive agricultural system that eventually looked something like this. Thank you.